All right, this should be our last Zoom class. I am cleared to go back to work on Monday, so I will be back in the classroom on Tuesday with you, live, masked up. We should hopefully get to see each other again. Okay, so today we're going to continue. First of all, I should ask, are there any questions? And I am recording this, and I'll post it as soon as I get it up on YouTube later today. All right, we're going to continue in our discussion of Chapter 3 on probability. And we're going to introduce two new terms, the term independent and mutually exclusive. What makes an event independent? What makes two events mutually exclusive? Okay, so remember, an experiment is you conducting whatever to get a series of outcomes. For example, you could flip a coin, and flipping a coin is an experiment. Now, the outcomes that you can get when you flip a coin is you can get a head or you can get a tail. So an event could be you getting a tail. So flipping a coin is your experiment. Your sample space, or the set of outcomes, we could call that S, and that's either you get a head or you get a tail. And an event is getting one or the other. An event could be getting a head. And we use capital letters to show events. So an event could be that you get a head when you flip a coin. So now when we look at events like getting a head, we can define events being independent or events being mutually exclusive, or they could be both at the same time. All right, let's get the definition. So first, let's look at a Venn diagram. And a Venn diagram is just a way for us to represent the sample space and then the events in an experiment. So the big rectangle represents your entire sample space. So the area inside the rectangle represents your sample space. And then the circles inside that sample space represents events. So this could be one event, and this could be another event. All right, so that's just one way we represent the outcomes of an experiment. So the outcomes of an experiment is our sample space, and then the events is whatever outcome we're interested in. Okay, so here's another picture of a Venn diagram. So again, the big rectangle represents our sample space, and the two circles represent our events A and B. And where these two events overlap is called the intersection of these two events. So where they overlap is the intersection. It's where one event overlaps the other, or where one circle overlaps the other. And this is called an intersection. We use the word and. So the English word we use for where those two sets overlap is and. So it's the elements that A and B have in common, A and B. And we use an upside down U to represent that space. So A upside down U and A and B mean exactly the same thing. So it's the two events where they occur at the same time. All right. For example, if you were looking at the events drawing a card from a deck, what's the probability of you getting a queen and a heart? So that's two events. The event of getting a queen, the event of getting a heart. What's the probability of getting a queen and a heart? All right. Now, when you look at this same Venn diagram, the area they share in common, the two circles share in common, is the intersection of those two events. So it's the probability of A and B occurring. The probability of A or B is the entire area of the two circles. So if I were to highlight that, that would be this entire area. So that's A or B. And A or B, an example would be if I draw one card out of a deck of 52, my events could be the probability of getting a heart, the probability of getting a queen. Those could be the two events. An A or B would be what would be the probability of me drawing one card out of a deck and getting a heart or getting a queen, one or the other. So an and type of probability is when both of them occur. And an or type probability is where you get one or the other occurring. And we have formulas for this. Okay, so again, wait till the slide comes up. From Tuesday, we got the conditional probability. And the conditional probability, B line A, is the probability that B occurs given A has already occurred. So that P parenthesis B bar A close parentheses is the probability that B occurs given that A has already happened. And the Bayes theorem for that conditional probability is the probability of A and B occurring, so both of them occurring at the same time, divided by the probability of A occurring. So in our Venn diagram, this would be the area, the probability of A and B would be the area of that slice that where they overlap, divided by the entire area of the circle A. And we can take this formula, for this Bayes theorem formula, and if we multiply both sides of this formula by the probability of A occurring, then we get a formula for the probability of A and B occurring at the same time. So the probability of an event A occurring at the same time of an event B occurring, so getting a heart and a queen, if you draw one card from a deck of 52, is the probability that you get a heart times the probability that you get a queen given you've already drawn a heart. So the probability of A and B occurring is the probability of A times the probability that B occurs given that A has already occurred. Okay, this looks way more complicated than it is, believe it or not. Okay, so what's the definition of events that are independent? And sometimes you can just think about the events and you know that they're independent. But two events are independent if the knowledge that one occurs does not affect the chance that the other occurs. Two events are independent if any of the three are true. If the probability that A occurs given B has already occurred is the probability of A, then these events are independent. If the probability that B occurs, given that A has already occurred, is equal to the probability of B occurring, then these are independent events. And the one that we probably see the most often, if they're independent, then the probability of A occurring and the probability of B occurring is just the product of the probability of A times the probability of B. And where we get that is from here. If they're independent events, then the probability of B occurring, given that A has already occurred, is just the probability of B. So if they're independent events, you can find the probability of both events occurring at the same time by just multiplying the two probabilities together. For example, independent events. The outcome of two rolls of a fair die are independent events because the second roll of your die is no way, no how dependent on what the first roll was. They're completely independent events. If I roll a die, I get a 2. Pick the die up and roll it again. The second roll is no way affected by the roll of the first die. Another independent, to show that two events are independent, all you have to show is one of these three things is true. If one of these three things is true, then the two events are independent. And if they're not independent, then they're dependent. Another example of independent events is the one that we've been using over and over again. If I flip a coin. So I flip a coin the first time. I pick the coin up and I flip it a second time. The second flip in no way is affected by what you got on the first flip. They're completely independent events. Okay. So sampling with replacement and without replacement. If you sample with replacement, so you take a sample and then you put that item back into your population and then sample again, then those events are independent. So if I have a bag that contains 20 marbles of different colors and I draw one marble out of the bag, note its color, and then put that marble back in the bag and then shake them up, mix them up real good again, and draw a second marble out of that bag, then the second trial is completely independent of the first. If I don't replace the marble, so I have a bag of 20 marbles and I draw one out and I don't replace it, I put it over to the side and then go back in and mix it up, I've changed the experiment because now I have less marbles in the bag. I only have 19 in the bag now. So the color I draw out the second time is actually dependent on the color I drew out the first time. So if I don't replace in my sample, by drawing my sample out of my population, that is dependent events. So independent is drawing with replacement. I put it back in and draw again. If I don't replace, that is dependent. So suppose you have a deck of 52 cards and you pick 3 cards with replacement. So the first card you pick out of the 52 is the Queen of Spades. You put this card back in the deck and you reshuffle the deck. And the reshuffling of the deck ensures the randomness of your second pick. And you pick another card now out of the deck after you reshuffled it, and you get a 10 of clubs. You take that 10 of clubs and you put it back in the deck and you reshuffle again to ensure the randomness of the third pick. And the third time you get the Queen of Spades again. And that is certainly possible because you put the Queen of Spades back in the deck. So these events are independent. Picking the Queen of Spades out the third time was no way, shape, or form dependent on picking the Queen of Spades the first time because you put it back in the deck. So when you replace, that is independent events. Getting a Queen of Spades the second time is completely independent of you getting the Queen of Spades the first time because you put it back in the deck. Being very slow today. Okay, now let's talk about without replacement. So you have your deck of 52 cards again, and you're going to pick 3 cards out again. So the first time you pick a card out of the deck, it's the King of Hearts. So you take that King of Hearts and you set it aside. Now you're going to draw a second card out of the deck. You've changed the criteria of your experiment when you don't replace, because now there are only 51 cards in the deck and there are only 3 kings in the deck. So when you draw the second card out of the deck, it depends on what you've drawn out the first time, because now your sample space is only 51. You only have 51 cards in the deck. So the second card, the 3 of diamonds, the probability of you drawing a 3 of diamonds has been affected by the fact that you've taken a card out of the deck and you didn't replace it. So you set this card aside. So now you've got only 50 cards in your deck. So you've changed your sample size again. So now you pick a third card and you get the Jack of Spades. So your pick was the King of Hearts, the 3 of diamonds, and the Jack of Spades. Because you've picked the cards without replacement, you're not able to pick the same card twice. And the probability of picking the second card is affected by what you picked the first time. You reduce your sample space each time. So without replacement, these events are dependent on each other. The probability of picking the 3 of diamonds is changed because you didn't put the King of Hearts back in the deck. Okay? Okay. I don't know what I can do about that besides fix my internet. I don't know if I can do that. Am I cutting out in and out with for everybody else also? I am recording this, so it should be okay as far as the recording goes, because it's going straight to my computer and not going through the internet. Okay. Let's look at an example. Thank goodness I'll be back on campus next week, and I don't have to rely on I live in the country, Wi-Fi internet. Just to complain a minute, where we live, literally right over there is a Cox cable. Right over there. But they did not bring Cox cable down our little gravel road. Right a half a mile up the road is an AT&T DSL line. So we live within a half-mile radius of DSL and Cox cable, neither of which we can get. the Cox Cable, they brought it up all the way from Highway 66, all the way up Wilshire, and then went back east to Blue Quail. But did they come our direction? No, because the Cox Cable guy said it would cost $50,000 for each house that we dropped a cable to. And it's just not worth the expense, you know, for a road that has 6 people that live on it, 7 people. Not very many. Anyway, so I have a deck of cards and I've shuffled it well. And if the internet says if you shuffle a deck of cards 7 times, that's a well shuffled deck. So suppose you draw out 4 cards from this deck without replacement. So you don't put the card back in the deck. You draw one out, then you draw the next one out, you draw the next one, you draw the next one. So which of the following 3 outcomes are possible? So the first outcome we have here is that I get the Queen of Spades, the 1 of Diamonds, the Ace of Diamonds, the Ace of Clubs, and the Queen of Diamonds. And that's certainly possible if I draw without replacement, because I have 4 different cards here. So I could do that. The second scenario says that I get the King of Hearts, the 7 of Diamonds, the 6 of Diamonds, and the King of Hearts again. I cannot get the King of Hearts twice if I'm drawing without replacement. So the second scenario is not possible. If the King of Hearts is out of the deck, I can't draw it a second time. The third scenario says that I get the Queen of Spades, the 7 of Diamonds, the 6 of Diamonds, and the King of Spades. And that is certainly possible because no card is being repeated. So I could certainly do that if I'm drawing from the deck without replacement. I could get the Queen of Spades, the 7 of Diamonds, 6 of Diamonds, and the King of Spades. But I can't get the second scenario because without replacement, I can't draw the same card twice. Now, with replacement, all 3 of these scenarios are perfectly plausible. All right, so that's independent events. What do we mean by mutually exclusive? Mutually exclusive events cannot occur at the same time. So A and B are mutually exclusive events if they cannot occur at the same time. This means that A and B do not share any outcomes, or the probability of A and B occurring at the same time is 0. So if we were to draw a Venn diagram, this means that there is no overlap in the 2 events A and B. They don't share any elements in common. So for example, if I have a sample space that consists of the numbers 1 through 10, and event A is getting a 1, 2, 3, 4, or a 5, and event B is getting a 4, 5, 6, 7, and 8, and event C is getting a 7 or a 9, then event A and B, the elements that A and B share in common would be 4 and 5. So events A and B are not mutually exclusive. They have elements in common. The probability of A and B occurring would be, well, there are 2 elements that A and B share in common. Over the sample space, there are 10 items in the sample space. So the probability of A and B occurring is 2 over 10. There are 2 elements, 4 and 5, that events A and events B share in common. However, well, and let's go ahead and finish this. A and B then are not mutually exclusive. They're not mutually exclusive because the probability of A and B occurring is not 0. Now, A and C are mutually exclusive events. Event A is getting a 1 through 5. Event C is getting a 7 or 9. A and C do not share any elements in common. Since they don't share any elements in common, there's no overlap of these two events, then the probability of A and C occurring at the same time is 0. So events A and C are mutually exclusive. So what makes an event independent? What makes an event independent is that it doesn't depend on the event that occurred before it. What makes two events mutually exclusive is that they can't happen at the same time. So if you roll a die, getting a 1 or a 2, those are mutually exclusive, because if you roll a die, you can't get a 1 and a 2 at the same time. Or if you flip a coin, getting a head is mutually exclusive from getting a tail. You can't get a head and a tail at the same time. You're going to get one or the other. So those are mutually exclusive events. Okay, so for example, if you flip 2 fair coins, flipping the coins is your experiment. What is your sample space if you flip 2 coins? Well, one coin could be a head and the other coin could be a head. So the first element in your sample space is they could both be heads. Or your first coin could be a head and your second coin could be a tail. That's the second element in your sample space. You could get a head tail. Or your first coin could be a tail and your second coin could be a head. That would be the third element in your sample space. You could get tail head. Or both coins could end up to be tails, and that would be the fourth element in your sample space. So there are 4 possible outcomes if you flip 2 coins: head, 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 tail, tail, head, or tail, tail. And each of these events are equally likely to occur if your coin is fair. Okay, so let's let A be the event of getting at most 1 tail, so no more than 1 tail. So A would consist of the set at most 1 tail, so no more than 1 tail. You could get a head head, that's not more than 1 tail, or you get a head tail, that's not more than 1 tail, or tail head. So the only outcome in the sample space that you would remove from event A would be getting 2 tails, because 2 tails is more than 1 tail, sorry. So the outcome head head shows 0 tails, head tail and tail head each show 1 tail. So A is the event head head, head tail, tail head. All right, let's let B be the event that I get 2 tails, all tails. So B can be written as the set tail tail. And since if I combine A and B and I get my sample space, then B is the complement of A. So the complement of an event is the stuff in the sample space that's not in that particular event. So since B consists of tail tail, and if I take tail tail out of my sample space, I get A. If I take it out of my sample space, what's left over is event A. Those 2 events are complements. So if I add them together, join them together, and I get the sample space, then the 2 sets are complements. The 2 events are complements. So we can write that B is the complement of A, which we write as A prime. We could also write that as A complement. So the probability of A occurring plus the probability of B occurring is the probability of A occurring plus the probability of its complement occurring, which is 1. So the probability of A, since event A contains 3 possible outcomes, divided by the total sample space would be 3/4. And the probability of B occurring, since there's only 1 outcome that satisfies B, that would be 1/4, because my sample space consists of 4 outcomes. Okay, let's continue this on. So again, flipping 2 coins. The sample space consists of, I could get a head-head, a head-tail, a tail-head, or a tail-tail. Let's let C be the event that I get 2 heads. Since B was the event of getting 2 tails, then the probability of me getting B and C at the same time is 0. I can't do that. I'm not going to get both a head-head and a tail-tail. So the probability of me getting B and C is 0. So B and C are mutually exclusive events. If I flip 2 coins, there's no possibility of me getting both 2 tails and 2 heads at the same time. They cannot occur at the same time. If they can't occur at the same time, they are mutually exclusive. Okay, so let's let D be the probability of getting 2 tails, or excuse me, the event of getting 2 tails, or getting more than 1 tail, sorry. If I get more than 1 tail, that means I get 2 tails. So the probability of D is 1 out of 4 because there's only one outcome out of the 4 where I get 2 tails. If E is the, got all these letters, if E is the event of getting a head on the first roll, which one do I have up here? Which sample outcomes in my sample space do I get a head on the first row? Well, this one and this one. So in this one, I get a head on the first row in the first outcome, and I get a head on the first row, roll, in flip, whatever it is, in the second outcome. So that would be that event A would be either head-head or head-tail. And the probability of event E occurring or getting a head on the first flip of my coin would be 2 out of 4. There are 2 outcomes where I get a head on the first flip. Find the probability of getting at least one or 2 tails in the flip. Well, if we look at our sample space, we got 3 outcomes where we get at least 1 tail. I could get a head tail, that would be at least 1 tail. A tail head, that would be at least 1 tail, or tail tail. So there are 3 outcomes in my sample space of 4 where I could get at least 1 tail. So the probability of me getting at least 1 tail when I flip 2 coins is 3 out of 4. All right, so this leads us to the 2 basic rules of probability. The first rule is called the multiplication rule. So if you run an experiment and A and B are 2 events in this experiment, 2 events defined on my sample space, then by Bayes' theorem, the probability of A and B occurring is the probability of B occurring times the probability that A occurs given that B has already occurred. So in symbols, the probability of A intersect B is the probability of A occurring times the probability that B occurs given that A occurs. Okay, so these are the same thing. Or if we solve for the conditional probability, we get the probability of both of them occurring divided by the probability of A. So the probability that B occurs, given that A has already occurred, is probability of A intersect B over the probability of A. However, all this explanation to say, well, what if these 2 events are independent? If these 2 events are independent, then the probability of B occurring, given that A has already occurred, is just the probability of B. So the probability of B occurring given A, it doesn't depend on whatever happens with event A. So the probability of B occurring given A is just the probability of B. So If two events are independent, the probability of A and B occurring, so the probability of A and B, is just the product of the probability of A times the probability of B. So for independent events, to find the probability of two events occurring, you just multiply the two probabilities together. Now, what if we have an OR type probability? The probability of A or B occurring. So I either get a head or I get, well, that's not good. I get a queen or I get a heart, one or the other. To find the probability of getting one or the other event occurring, you take the probability of A and you add the probability of B, and you subtract off from that the probability of both occurring at the same time. If the events are mutually exclusive, then A intersect B is 0. So for independent events, the intersection probability of A and B occurring is the product of the two probabilities. But if they're mutually exclusive, that's 0, because they can't occur at the same time. Two events are mutually exclusive if the two events cannot occur at the same time. So if that A probability of A and B is 0, then you get this formula down here. So for mutually exclusive events, the probability of A occurring or the probability of B occurring is just a sum of the two probabilities. So if we have independent events, the probability of A and B occurring is the probability of A times the probability of B. If we have mutually exclusive, they can't occur at the same time, then a probability of A or B is the sum of the two probabilities. So Juan is trying to choose where to go on vacation. His two choices are New Zealand and Alaska. So we're going to let event A be that he goes to New Zealand. Well, that'd be a nice vacation. We're going to let B be the event that he goes to Alaska. Now, Juan can only afford one vacation. He can't afford two. So he can either go to New Zealand or he can go to Alaska. He can't do both. So let's say, weighing all his options, the probability that he's going to go to New Zealand is 0.6. There's a 60% probability he's going to choose New Zealand for whatever reason. The probability that he chooses to go to Alaska, weighing all the options, is 35%, 0.35. Now, the probability that he goes both places is 0 because he can't afford two vacations. So the probability that he goes to New Zealand and Alaska is 0. He's not going to do both. So the probability of A and B is 0. So what's the probability that he goes to one or the other place? Well, since these are mutually exclusive events, he's not going to both of the destinations. He's only going to go to one or the other. So the probability of him going to New Zealand or Alaska will be the sum of the two probabilities. Because this probability A and B is 0, he's going to subtract off 0. So the probability he goes to New Zealand or Alaska is the sum of the two probabilities. 0.6 plus 0.35 is 0.95. So there's a 95% chance he's going to go someplace, New Zealand or Alaska. And then that would mean then there's a 5% chance that he doesn't go either place. So the probability of him not going to New Zealand or Alaska is 1 minus the probability that he goes to one or the other. So it's 0.05 or 5%. So these are mutually exclusive events. Okay, let's look at another example. So a student goes to the library, and there are two events that we're describing. The first event we're going to call B, and that's the event that he checks out a book. So B is this student checks out a book. The event D is the event that the student checks out a DVD. Does anybody check out DVDs anymore? So event D is that he checks out a DVD. So the probability that he goes to the library and he actually checks out a book is 40%. So 40% of the time when he goes to the library, he actually checks out a book. The probability that he checks out a DVD is 30%. So it's 30% of the time when he goes to the library, he actually checks out a DVD. The probability that he checks out a DVD, given that he's already checked out a book, is 50%. So apparently, these are not independent events, because when he checks out a book, then the probability of him checking out a DVD is affected. So the probability of him checking out a DVD, given that he's already checked out a book, you think, I'm checking out a book, I can check out a DVD too. So the probability of him checking out a DVD, given that he's already checked out a book, is 50%, 0.5. So let's find the probability that he checks out a book and a DVD. Let's find the probability that he checks out one or the other, a book or a DVD. So according to Bayes' theorem, the probability of checking out a book and a DVD can be found by multiplying the probability of checking out a book times the probability that he checks out a DVD, given he's checked out a book. And that is 50%. So if we multiply those two probabilities together, the probability of checking out a book is 40%, 0.4, times the probability that he checks out a DVD, given he's checked out a book already, is 0.5, we get 20%. So the probability of him checking out a book and a DVD is 20%, 0.2. What's the probability of him checking out one or the other, a book or a DVD? Well, according to our formula that we got earlier, to find an OR-type probability, we add the two probabilities and we subtract off the probability of both of them occurring at the same time. Now, these are not mutually exclusive. And they're not because the AND probability is not 0. So the probability of B or D occurring is the probability of B plus the probability of D minus the probability that both of them occur at the same time. So that would be 0.4 plus 0.3 minus 0.2, which we just calculated, which is 50%. So the probability that he goes to the library and checks out a book or a DVD is 50%, 0.5. All right. Studies show that one woman in 7, approximately 14.3%, who live to be 90 will develop breast cancer. Suppose that of those women who develop breast cancer, a test is negative 2% of the time. Also suppose that in the general population of women, the test for breast cancer is negative about 85% of the time. Let B equal a woman develops breast cancer and N equal that the person tests negative. So suppose a woman is selected at random. What is the probability that the woman develops breast cancer? What is the probability that the woman tests negative? So we're going to let, from this example, we're going to let B be the event that a woman develops breast cancer. So according to the information that we are given, the probability of a woman who lives to age 90 developing breast cancer is this 14.3%. And we normally write a probability as a decimal. So the probability that a woman who lives to the age of 90 develops breast cancer is 0.143. So they gave us that information. Okay, so N is the woman tests negative. And they tell us that the test for breast cancer is negative about 85% of the time. So the probability that a woman tests negative is the 85%, which we write as a decimal, 0.85. Okay, so that's the information the problem has given us. So what are they asking? What's the probability that a woman develops breast cancer, which we found? What's the probability that a woman tests negative, which we found? So the probability that she develops breast cancer is 0.143. The probability that she tests negative is 0.85. Okay, let's continue this problem. Given that the woman has breast cancer, what's the probability that she tests negative? So what we're looking for is the probability that she tests negative given she has breast cancer. So the way we write that, the probability that she tests negative given that she has breast cancer. That's what that symbol means. So that's the probability that you test negative given that you have breast cancer. And using the information that we have up here, it says that suppose that of those women who develop breast cancer, a test is negative 2% of the time. So they tell us that this is 2%. There's a 2% chance that you're going to test negative given you have breast cancer. Okay, so now we have a lot of stuff here. So we have been given the probability of a woman developing breast cancer. We're given the probability that she tests negative, and we're given the probability that she tests negative given that she has breast cancer. So now we can find some other information about this experiment. What's the probability that the woman has breast cancer and tests negative? So the probability that she has breast cancer and she tests negative. So we would write that as a probability that she tests negative and she has breast cancer. Or we could write this as the probability that she has breast cancer and she tests negative, which is probably the way we want to write it if we're using Bayes' theorem. Okay, and I'm going to have to write over here. I've got the Zoom stuff in my way here. So the probability of B, and I'm going to write this in intersection notation just to save space. According to Bayes' theorem, the probability of B and N occurring is the probability of B occurring times the probability that N occurs given B. And that formula over here on the right is Bayes' theorem, which we've looked at several times. So I can figure out the probability of having breast cancer and testing negative, which would be a bad thing. To have breast cancer and test negative, a bad thing, because you want to test positive if you actually have the cancer so you can start treatment. So the probability of having breast cancer and testing negative is the probability of having breast cancer, which is the 0.143, times the probability of testing negative given you actually have breast cancer, which is 0.02. So if we take our calculator out and we multiply 0.143 times 0.02, we get 0.0029. So there's a 0.29% chance that you have breast cancer and you test negative. So it's a pretty small percentage that's going to have breast cancer and test negative. So again, where did I get that the probability of B and N is the probability of B times the probability of N given B? That's Bayes' theorem. And that's probability of B and N occurring is 0.143 times 0.02, which is 0.0029. All right, what's the probability that the woman has breast cancer or tests negative? So we have an or here. So the probability that she has breast cancer or she tests negative. So we could write this as the probability of B union N. And from our formula earlier, the OR type probability, we add the two probabilities together and we subtract off A intersect B. And these are not mutually exclusive events. A woman can test negative and have breast cancer, so they're not mutually exclusive. Both of the things can happen at the same time. That P, the probability of A and B occurring, we just calculated as 0.0029. So the probability that a woman has breast cancer was given to me. The probability that she tests negative was given to me, minus the probability that I calculated that both of those things occur at the same time. So the probability of me having breast cancer or testing negative, my handy dandy calculator says that's 0.9901. Or there's a 99% chance that one or the other could occur. I don't know why I'd be interested in one of the other occurring, but I could. And then I just said this just a second ago. Are having breast cancer and testing negative independent? No, they're not independent. They're not independent because if we look at the definition of independence, independence says that one of three things has to be true. Since the probability of testing negative is 0.85 and the probability of testing negative given that you actually have breast cancer is 0.02, the probability of N given B is not equal to the probability of N. And for these to be independent events, that has to be true, that the probability of N given B has to equal the probability of N. Are they mutually exclusive? And I already answered this. The answer is no, they're not mutually exclusive, because the probability of having, where did I get A and B? Why aren't you yelling at me? That should be B and N. I don't know where the A and B came from. It's been one of those days. But they're not mutually exclusive, because both events can occur at the same time. You can have breast cancer and test negative. For them to be mutually exclusive, they can occur at the same time, but they can, because the probability of B and N occurring at the same time is 0.0029. So they're not mutually exclusive. They can happen at the same time. Okay, so here, this is an example of finding an and an or type probability given some information. And what you're given is two probabilities and then a conditional probability. You're given the probability of developing breast cancer. You're given the probability of testing negative. And you're given the probability that, my brain just went dead. You're given the probability that you test negative and that you have breast cancer. Just negative. That was what this one was. Sorry, brain's going dead. Test is negative 2%. 85. Probability of testing negative is 85%. I thought I was going to get through this class without making a mistake. All right. Contingency tables. What a contingency table does for you is it's just a way of organizing information in a table. And that's exactly what it is. And what it helps us with is developing conditional probabilities. So the table displays sample values in relation to two different variables that may be dependent or contingent on one another. Okay? So here is an example of a contingency table. So this is a study that compares speeding violations and cell phone use. So what they did is they looked at 755 people, and they determined whether the person uses a cell phone while they're driving. Did they get speeding violations while they drove? So the first row here in this table is the people who use cell phones while driving. So 305 people used a cell phone while they were driving. So 305 people out of the 755 used a cell phone while they were driving. The people who didn't use a cell phone is the second row. So there are 450 people who do not use a cell phone while they drive. So out of the 755 people, 305 of them use a cell phone while they're driving. At some point while they're driving, they use a cell phone. Of the 755, 450 said they didn't. They don't use a cell phone while they're driving. All right. So that's the rows. What are the columns? Well, the columns are whether or not they received a speeding violation. So the first column is the number of people who received speeding violations. So 70 out of the 755 people actually got a speeding ticket during the year. 685 didn't. They didn't get a speeding ticket. That doesn't mean they weren't speeding. It just means they didn't get a violation for their speeding. So you'll see that the two values down here and the two values here both add up to 755. Now, what you have in the cells in your table is how many people are doing both. So, for example, 25 people were using cell phones and got caught for speeding. So they got a speeding violation and they were using a cell phone. 280 people were using their using their cell phone, but they didn't get a violation. So 25 and 280, 305 people were using their cell phone. In the second row, 45 people got a speeding violation and they were not using their cell phone. They got a speeding violation and they were not using their cell phone. And 405 people were not using their cell phone and they didn't get a speeding ticket. So that's what a contingency table does. And these values inside show us both of them occurring at the same time. So 25, they're using a cell phone and they got a speeding violation. 45 were not using their cell phone and they got a speeding violation. 280 were using a cell phone and did not get a speeding violation. And 405 were not using their cell phone and they did not get a speeding violation. Okay, so now using this contingency table, let's see if we can find some probabilities. What's the probability that a driver is a cell phone user? Okay, so how many people use a cell phone? Well, my survey says that 305 people in this survey were using a cell phone. So the number of outcomes of people using cell phones is 305. All right. What's the total possible outcomes? What's the total number of people I surveyed? And that's 755. So 305 out of 755 are cell phone users. Okay, so that's the probability of a driver is a cell phone user. 305 out of 755, whatever that equals. Okay, what's the probability that a driver had no violation in the last year? Well, how many people did not have a violation? It looks like 685 did not have a violation. So the number of outcomes in this survey, the number of people who didn't have any kind of speeding violation is 685. Out of the total number of people that we surveyed, 755. So 685 out of 755 did not have a speeding violation. All right. So we got all this information just from this contingencies table. Right. So what's the probability that a driver had no violation in the last year and was a cell phone user? So let's look at our contingencies table. So where do no violation and cell phone user intersect? So this is the no violation column. This is the cell phone column. So it intersects at 280. So 280 people had no violation, but they were a cell phone user. So 208 out of the 755 So the probability that you were a cell phone user and you didn't get a violation is 208 out of 755. Okay. What's the probability that a driver is a cell phone user or had no violation? So the or type probability means that we're going to use that formula for the or. So that would be the probability that they had a cell phone or no violation. So that's the probability that they use a cell phone plus the probability that it didn't have a violation minus the probability that both happened. C and N. Okay, so what's the probability that the driver is a cell phone user? Well, how many cell phone users do we have here? 305. So 305 of them were cell phone users. Okay, how many of them had no violation? Well, that's the 685, right? Okay, and let's subtract off from that how many had used their cell phone, but they didn't have a violation. You seeing, is that the 280? So the 280 used their cell phone, but they didn't get caught for speeding. So that's the 280 maybe minus 7 over 755. So the probability of one or the other is the sum of the two probabilities minus the probability that they both occur at the same time. And you can use your cell phone and not get a violation. 280 people did this, whatever that equals. Using arithmetic, that's 710 out of 755. Right? What's the probability a driver is a cell phone user given the driver had a violation? Well, who had violations? That's this column here. So that is the violation column. So what's the probability that the driver used a cell phone given they had a violation? Well, 25 of them were using a cell phone that got a violation. And how many of them got violations? Well, 70. So again, you can see a conditional probability, the sample space is reduced. The sample space is not the 755. The sample space is the 70. 25 out of the 70 were using a cell phone and got a violation. So the probability of using your cell phone given that you had a violation is 25 out of 70. Okay, find the probability that a driver had no violation given the driver was not a cell phone user. So who are my no violation? Well, that's this column. That's my no violation people. So my denominator is going to be 685. And what am I interested in? I'm interested in the people that had no violation given they were not a cell phone user. Well, who's that? That's this 405. So 405 people were not using their cell phone and they didn't get a speeding violation. So the people that are had no violation given that they weren't using a cell phone is the 405. So that's going to be 405 over the 685. Oh, wait a minute. Oh, golly goobers. No violation in the last year and was not using a cell phone. Not using a cell phone and no violation. So that's 405 out of 450. I hope you were yelling at me silently. So the probability that a person had no violation given that they were not a cell phone user. So the row, not a cell phone user, is that row that I've circled. That's the row. And the number of people who had no speeding violation, given that they were not using their cell phone, there's 405 out of 450 who are not using a cell phone at all while they're driving. So it's 405 out of 450. I can't blame it on COVID too much longer, can I? I think that's going to be a good place to stop. That is a good place to stop, because the next topic is the last topic in this chapter, tree and Venn diagrams. And we will pick that up in class. You'll see each other face to face on Tuesday. Are there any questions? All right, I will see you Tuesday. Have a good rest of your week.